Expected value is one of these topics that anytime we talk about probability and random variables, expected value is one of the first things you might want to know about a random variable that you're getting to know for the first time. It's one of the first things you're going to want to know about a random variable. And I'd like to introduce it by thinking for a moment, doing a little wishful thinking about the lottery, specifically the Powerball. So with the other people in your team, what I'd like to discuss is the open-ended question: is it worth it to buy a Powerball ticket? So take about 60 seconds, talk with the people in your team, and see if you can come up with at least one reason why the answer to that question might be yes, and at least one reason why the answer to that question might be no. Is it worth it to buy a Powerball ticket? Take about a minute and see what you come up with the other people in your group. So what were some of the things you said about, yes, it is worth it to buy a Powerball ticket? What were some of the yes because that you came up with? You could win a bunch of money. Okay, sure. I mean, I think if that weren't the case, nobody would play the lottery, but let's say millions. Tends to be your typical grand prize, right? Okay. Yeses? Yeah.
Tickets are cheap.
Tickets are cheap. Anyone know how much a Powerball ticket costs?
Like $2.
Yeah, it's $2. Last time I checked, anyway. So, yeah, that's pretty inexpensive in the grand scheme of things. What else? What are some other good yes reasons? What were some of your no reasons?
It's very unlikely to win.
It's unlikely that you're going to win those millions. Right? There are other smaller prizes that you can win in Powerball. They get a little bit less front page press, right? But for matching a couple of the numbers, you could win smaller prizes. Right? But even then, you're probably pretty unlikely. Were there other reasons that you said for no, why it's not a good idea to play Powerball?
You could get like addicted to playing.
Okay, that is certainly a possibility. It's one of the reasons that lotteries and other gambling is sometimes seen as not a public good necessarily because of the possibility for addiction and all the things that come along with that, right? So the big casino fight that's going on in Massachusetts right now, the possibility of addiction is one of the biggest reasons why I think politicians are against casinos. Right? So there's kind of a balancing act here in deciding whether or not you're standing in that line at the Tedeschi or whatever, whether you want to spend the money for that Powerball ticket. And it's kind of this tug between two opposing forces. On the one hand, you're not very likely to win at the end of the day. The chances that you're going to hit that Powerball jackpot are pretty small. So that's kind of on the bad side of the balance sheet. But on the good side of the balance sheet, you could win millions of dollars. So there's this one force that says, yes, this is a good idea to play. There's this other force that says, it's probably not going to happen for you. But what we'd like is we'd like to come up with as rational a decision as we can make about whether or not to play the lottery. And that rational decision has to take into account this third feature. Right? Not just the fact that we could win millions of dollars or that it's not likely to win. Each of those is taking us to one camp or the other. But the fact that the tickets cost money to play is actually important. Right? If tickets were free for Powerball, what would the choice be? Yeah, absolutely. Let's play it. If it costs me nothing, then sure, I'll take 100 million tickets right now, please. Right? Increasing my odds dramatically that I might win the jackpot. But tickets are not free. On the other hand, what if tickets cost, I don't know, $1,000 a piece? A lot of people. So you're shaking your heads no. It's probably going to change the calculus for a lot of people that play the lottery if tickets suddenly went up to $1,000 a piece. Right? In that case, the answer is clearly no. Because the benefit ratio is just not there. If it costs me too much money for a chance at winning this $1 million, or whatever it is, then it makes it a worse idea. We want to find that balance point in the middle. Why is $2 a good price point? Why shouldn't it be maybe $1 or $5 or something? So that's what we're going to get at today, is how to balance the value of an uncertain quantity that we call a random variable. In this case, it would be the amount of money that you win if you play the Powerball. Balance the value, the possible value of that unknown quantity, with the likelihood that that variable takes that gigantic value or that zero value or whatever it is. So that's where we're headed. But the Powerball is kind of tough. So let's talk about a simpler game. in this game, I flip a single coin, and we're going to assume that the coin is fair. What is the sample space for that experiment? Reaching back to some of your prior vocabulary. If I flip a single fair coin, yeah, so the sample space is the set of possible outcomes that could happen in this experiment, and there are only two when I flip a regular coin, heads and tails. Okay? So we call that set the sample space for this experiment. Now, if my coin is fair, what does that mean about those two outcomes? When I say I have a fair coin, what am I talking about? What is fairness here? Yeah.
It has an equal likelihood of happening.
Right. Each of the outcomes in my sample space here, the heads and the tails, has an equal likelihood of happening. So what would we say is the probability of getting a head? Yeah, 50%. And the probability of getting tails? The same 50%. So this is a complete sort of probabilistic description of the problem, of the game here. We have two possible outcomes, heads and tails, and the probability of each one of those outcomes is right here, 50% each. Well, this isn't really a gamble yet. In order to make it into a gamble, we have to make things interesting. Let's make this coin flip interesting. By giving each of the outcomes in this list, each of the events in my sample space, each of the outcomes, a particular dollar value that you could win. And I'm going to do it this way. If the coin comes up heads, then you win $1. If the coin comes up tails, you win nothing. You walk away. Now let's imagine that this game is free to play. Is it worth it?
Yeah.
Why? Why is it worth it?
Because it's likely that you could win.
It's pretty likely that we could win, right? It's 50-50, but it's pretty likely. And why is the cost important?
Because it costs nothing, so you don't lose anything.
Right, we're not exposing ourselves to any risk here, right, by playing the game. We have no skin in the game, as they would say, right? If it costs me nothing to play, it's a good idea to play. Because I might win $1, which is great, or I might win nothing, in which case nothing ventured, nothing gained. Right? So if this game costs me nothing to play, it's a good idea. All right, what if I raise the stakes? What if the game costs you $1 to play? Worth it? Not worth it? Keep in mind here, I should be specific. When it says that this is the amount that you win, this is just the amount that you get back from me after playing the game. So if you pay me $1 first, then if the coin comes up heads, you get $1 back, not $2. It's not on top of what you bid. It's the total amount that's going to come to you after you play the game. So first you pay me, then we flip the coin, then I give you one of these two amounts of money. So if you pay me $1 to play, and then you might get $1 back, or you might get nothing. Is this a good idea?
No.
No. Why is this a bad idea?
You don't win anything.
Yeah, even in the best case scenario here, you're just going to get the $1 back that you paid to play and net nothing out of the game. The worst case scenario is you pay me $1 to play and then you get nothing if the coin comes up tails. So here, it's definitely a no, right? This is certainly not something that we want to do because even in the best case scenario, you're just breaking even. So you're exposing yourself, what you would say, to a lot of risk. All right, let's change the price again. What if it costs you $0.25 to play? Now are you going to take this wager? Okay, you could actually make something from this quarter, right? So the possibility of a profit is there. What we could do is we could just add kind of the amount of profit as a third column here. Profit. So my profit, if I win, is going to be 75 cents because I paid 25 cents to play and then I won $1 if the coin came up heads. On the other hand, my profit's going to be negative 25 cents if I paid that quarter and then the coin came up tails, right? But the potential upside here is greater than the potential downside. I could win 75 cents out of this, or I could lose a quarter. Right? So there's kind of a balance going on there. It feels like a quarter is better, is more worth it to pay for this game than $1. What if you have to pay 75 cents for this game? Now you're back to no. Why is that? Yeah, again, looking at the potential upside, even if you win this wager, you're going to end up netting a quarter of profit, 25 cents. Where if you lose this wager, you're going to be losing 75 cents worth of profit. So probably with a 75-cent wager, this is not a good idea, again. All right, well, you probably see where I'm going with this. What if it costs you 50 cents? Are you going to play, or are you going to walk away? I saw some shaking heads. I saw some shaking hands. So what's that all about?
Maybe.
Maybe. Okay, why maybe?
Because you get half that if you win.
Okay. So if you end up winning, then the profit that you make is 50 cents. If you end up losing, then the profit that you make is negative 50 cents. So now my choices are I could win 50 cents of profit out of this, or I could lose 50 cents of profit out of this. So the potential upside and the potential downside are actually the same here. Okay, why does it matter that this coin is fair? What does that do with your decision? Let's suppose that I am using a secretly weighted coin that comes up tails 90% of the time. Then what? My coin is rigged. It's much more likely to come up tails. Now, how does that change your decision? Now you're back to no, right? Because there's a much greater chance of seeing this negative 50 cents worth of profit compared to the positive 50 cents worth of profit. On the other hand, if I have a coin that comes up heads 90% of the time, now you want to play because it's far more likely that you're going to see this positive profit compared to the negative profit. So just like you were talking about with Powerball, making the decision of whether or not to play requires weighting the possible outcomes, the possible values of your winnings, against the likelihood of those outcomes happening. And if my coin is fair, then each of these outcomes is equally likely. And each of them exposes us to the same amount of potential upside and downside. So I think I agree that under a fair coin, with $1 on heads and nothing on tails, 50 cents makes it completely up to you, right? There's not a strong rationale for playing because you might make a profit, and there's not really a strong rationale for not playing because you might, right? So that's kind of a tipping point, a break-even point. So let's look at the structure of this game a little bit more closely and begin to bring some of the vocabulary from the course back into it. So we have to balance two things: the amount that you could win in each possible outcome of the game, which, because we don't know how much that's going to be before we play, we call that a random variable. I'm going to call that variable capital W. So capital W represents the winnings that you could make in this game. But then we have to weigh those possible amounts against the likelihood of those outcomes actually happening. Right? So the probability that W will equal each of these possible amounts. And so on the one hand, we have the probabilities that are attached to the different outcomes in our sample space. Heads and tails are the two outcomes in the sample space. Each one of them has a probability of 50%. But then what we're doing now is associating to each one of these outcomes a certain number, numerical value. That's this random variable, winnings, capital W. And because each of the values of W relates to one of the outcomes in the sample space, those values of W have probabilities as well. What can we say about the random variable W, our winnings? Well, it's $1 with a probability of 50%, or it's $0 with a probability of 50%. And that's the data right here that we're going to need to balance in order to determine whether or not to play this game. And so here's the question I want to ask now. On average, what's going to happen when we play this game? If we play the game once, then either we're going to win $1 or we're going to win nothing. So those are the only two possibilities. But what happens if we play this game twice? If you were to play this game with me twice, what are the possible amounts of money that you could win in total?
You could win $2.
Yeah, we could win nothing if we lost the game twice. We could win $2 if we won the game twice. Or we could win $1 if we won once and lost once. So if I play the game twice, I'm going to expect to win either 0, 1, or $2. And now here's the key. I'm asking the question, what happens in this game on average? So what I want to do is not answer the question, how much could I win total, but how much per game could I win? If I play the game twice, I could win 0, 1, or $2. How many dollars per game does that correspond to? $0 if per game if I lose twice. $1 per game if I win twice. Or how much per game if I win once, lose once? If I win a total of $1 over 2 games, what's my average winning? 50 cents. Right? So I'm just going to divide those numbers by 2. So if I play the game twice, then my per game winnings are going to either be 0, 50 cents, or $1. What if I play the game 4 times? Well, it's going to go down. Some of the outcomes are going to go down a little bit lower. Some of them are still going to be high, right? There's a chance I could still win all 4 of these games and get a total of $4 out of it. I could lose all 4 games and get a total of 0. But if I divide each of these by 4 to find out how much per game I'm going to get, here are the amounts that I'm going to get per game. But now my question is, which of these amounts is most likely to happen? If I play the game 4 times, let me ask it this way. What's more likely? That I win $1 per game, or that I win $0 per game? Between the 2 of those outcomes, which one is more likely?
Zero.
Why?
Because every game that you play, the chance of winning, probability-wise, gets like smaller and smaller.
It does?
I don't know. I can say.
Let me throw that out to the room. So every time you play this game, what is the probability of winning? 50%. So when I play the game the first time, my chances of winning are 50%. When I play the game the second time, my chances of winning that second game are 50%. Chances of winning that second game are 50%. The chances that I win the third game that I play, 50% again. Chances that I win the fourth game, 50%. Right? Every game is its own individual entity. Right? Nothing changes from one game to the next about the game itself. That's a statistical property that we call independence that we're going to talk about on Wednesday. And if that's the case, if every time I play I have a 50% chance of winning, what's the difference in probability between winning nothing over 4 games and winning $1 every game? In other words, winning all 4 games. I'll look at it this way. Winning none out of my 4 games, or is this all 4 out of my 4 games? What's more likely? Neither. Those are both equally likely. Right? If my chances of winning each game are 50%, then it's a toss-up. You know? Winning all 4 is the same probability as losing all 4, because winning and losing have the same probability in this model. Okay, but now let's suppose that I look at the other outcomes in the middle. Winning once or winning 3 times or winning twice. Which one of those outcomes is most likely to happen, do you think? Twice. Why is twice the most likely outcome to happen in this game? Yeah. Because it's in the middle, and the probability of winning and the probability of losing are the same. So, of all of these possibilities, I would say that the most likely to happen would be that I win 50 cents per game. Right? If I play this game 4 times, and my chances of winning each of those games are 50-50, then it's probably most likely that I'm going to win half of the games that I play. Right? 2 out of the 4. And if I do so, then I'm going to end up with 50 cents per game. So what happens if we play the game instead of 4 times, we play it 1,000 times? If we play the game 1,000 times and we have a 50-50 chance of winning each one, then how many times do we expect to win on total? Half of the 1,000, or 500 times. And if I play this game 500 times and I win it 500 times, sorry, if I play it 1,000 times and I win it 500 times, how much money have I made in total? Every time I win, I make $1. So I would expect if I win half of these 1,000 games, then I'm going to make $1 for each of the 500 times that I win. So I expect to win $500 in total. How much per game does that end up being? $500 over 1,000 times? 50 cents per game. Hey, there's that 50 cents again. Right? So on average, we expect to win this game half of the times that we play it. So the more that I play it, the more convinced I am that half the time I'm going to have won. And if I win half the time, then I'm going to get $1 half the time and $0 the other half the time, which in the end averages out to 50 cents per game. So, on average, is this game worth playing? That depends on how much you pay to play. Right? You should only decide to play this game if it's going to cost you less than you expect to win, on average. Right? Paying $0 to play this game is a no-brainer, because we know for sure that we're going to make a profit. Paying $1 to play this game is also a no-brainer that we don't want to. because we're guaranteed not to make any profit. But in the middle between those two possibilities, the one that makes it a toss-up is that 50 cents per game. On average, it's only going to be worth playing if it's going to cost us less than 50 cents per game to play. So what does this have to do with the topic of the day? Here's our definition. The definition goes like this. If x is a random variable, so in our previous example, that random variable was the amount of winnings that we can make by playing this game, then we're computing a quantity that's called the expected value of the random variable x. And it's denoted by this notation E of x. So this capital E stands for expected value of x. And we define it to be, just like we have been doing, the average value that this variable takes over a large series of repeated trials. It's like the average amount of money that we would win if we played this game a whole bunch of times. Right? Then the average amount that we win per game is what we would call the expected value. And I'm going to unpack this notation in just a second, because it looks a little intimidating, and so we've got a little bit of work to do to unpack what it's doing. But here's what I find is the clearest way to understand how to compute an expected value. Let's go back to our dice game again. We decided that the expected value, the expected amount that we would win, which we would now denote as E of W, was 50 cents. Now, how could we have gotten that from the information that's in this table up here? This information is telling me how much my winnings are and what is the probability of each amount of winnings. Well, my probabilities are telling me I'm going to win half the time and not win the other half the time. For those times that I win, how much money am I making per game? Well, every time I win, I make $1. And if that happens half the time, then I'm going to end up with a 50 cent per game average coming from the times that I win. And on the other hand, from the times that I lose, I'm going to end up with a $0 per game average coming from my losses. So notice that all I did there was just multiply. My $1 winnings times the 50% of the time that I win gives me the 50 that's over there. And then from my losses, $0 multiplied by the 50% of times that I don't win gives me the 0 that's in this column over here on the right. So all I did was I multiplied the winnings by their probabilities. And then what do I do to that to get my expected value? I just added those up. Over time, I'm going to have some wins and I'm going to have some losses. And on average, my wins are going to contribute 50 cents per game to my outcome. On average, my losses are going to contribute $0 per game. And so when I add them all together, the total, my expected value for my winnings, is 50 cents. So this little table helps us to unpack what's going on in this formula down here. So let me unpack that. We'll look at one more example together, and then we'll do some examples in your individual groups. So the first thing you look at when you look at this notation, I'm going to leave this scary symbol over here to the end. So let's just look at what's on the inside of this notation for the moment. So blur that part out. So what am I doing? I'm multiplying here a little x by a probability. The probability that capital X, which is my random variable, is equal to little x. This is one of the most unfortunate notations in all of statistics because you're using both capital letters and small letters at the same time. But all that we're doing is taking the possible values that this random variable can have, so the amounts that are in this column, and we're multiplying them by their respective probabilities. Probability that capital X is equal to little x. That's what's in this column. So the x's come from here. That tells you, again, the amounts that this variable can have, the amounts that you could win in our winnings example, the amount of the variable. And that's being balanced against the probability of taking that value. And the way that we're balancing it, probability of getting x. The way we're balancing it is by taking what is in essence a weighted average. We're averaging out each of the possible winnings amounts by the probability of seeing that winnings amounts. And we've just multiplied straight across to get each of those numbers. So the first thing we did here was multiply across to get 50 cents, multiply across to get $0. And then once we've multiplied across, what did we do at the end? What did I do with this 50 cents on the right and this 0 on the right to get my final expected value?
Added them.
We added them. And that's all that this scary bit of notation here is telling you to do. This capital Greek letter sigma stands for sum. S is for sum. And it just means to take the values that you got here when you multiplied the amounts by their probabilities and just add them all together. Okay? The sum is taken over all possible values that this random variable could take. So as long as we've accounted for every possibility here, then multiplying the possible value of the variable by its probability and adding up all of those results will give you the expected value of that random variable. So here's a more complicated example. We're going to roll 2 dice instead of flipping a coin this time. And if the total on those 2 dice comes up as either 7 or 11, then you're going to win this game. You get $10. If it doesn't come up as 7 or 11, then you win nothing. And the question again is, how much are you willing to pay this game? Which is the same question as, how much could you expect to win on average if you played this game a whole bunch of times? What would be a fair price to pay, which is equal to the amount that you would expect to win in this game over time? So just to get you set up on this one, we're going to let x be the random variable. It represents the amount that you could win by playing this game. So it's going to either be 10 or 0. Okay. X is going to be 10 if the sum of the dice comes up as 7. It's going to be $10 also if the sum of the dice comes up to be 11. And it's going to be 0 if the dice comes up as anything other than 7 or 11. So what information do we need in order to finish determining the expected value in this problem? What do we need to know?
Possibilities you have, like outcomes.
Okay, so I've left some blank spaces up here because the outcomes that give us 7 on dice and the outcomes that give us 11 on dice don't account for all the possible outcomes in your sample space. So we need to know what those outcomes are. And what do we do with that information? What else is blank on this table that we're going to need to know?
The other possibilities that you can get.
Well, that's
Besides
this.
7 and 11.
Okay, that's this row here on the bottom. So the other possibilities are everything from 2 through 12 except for 7 and 11. So 2, 3, 4, 5, 6, 8, 9, 10, and 12. That's covered in the anything else category. But once we know what those possibilities are, what else do we need to know in order to make this decision about expected value?
The probability.
Yeah, right. We need to know what the other possibilities are for the sake of knowing how probable those outcomes are. We need to know how likely it is that a 7 or 11 comes up versus anything else. And once we find them, then computing the expected value is fairly quick. All we'll have to do is multiply across the values by their respective probabilities. So $10 times the probability of rolling a 7, $10 times the probability of rolling an 11, and then $0 times the probability of absolutely anything else happening. So the first thing we're going to do in this expected value problem when we get there is we're going to multiply straight across. So this column is what I'll call x times the probability that capital X is equal to x. This is a capital X here. So we're going to multiply across once we get those probabilities. And then, once we get all of those, we'll add them together to get our expected value. So that's the recipe for finding an expected value. Once we have those probabilities, if those probabilities are given to us in the beginning of the problem, then it goes really quickly. In this example, we have to do a little bit of work to find those probabilities ourselves. So here's the sample space for rolling 2 dice, right? A red die and a green die. There are 36 possible outcomes because each dice can come up as 6 different things, and so 6 times 6 gives us 36. And if there's 36 outcomes in my sample space, all I need to do, because each of those 36 outcomes is equally likely if the dice are fair, I just need to figure out how many of them result in a 7 and how many of them result in an 11. What's one example of a dice roll that gives us 7?
1 and 6.
1 and 6. So this outcome up here in the upper right-hand corner, that's 1 and 6. So there's one outcome that gives me a 7. What are some others?
2 and 5.
2 and 5 is one. 3 and 4 is another. 4 and 3, 5 and 2, and 6 and 1. So all of the outcomes that give us a 7 are found in the sample space right here along this diagonal. How many of those outcomes are there?
Twice because technically there's 2 dice.
That's right, there's 2 dice, and if we color one red and the other green, we can see why 1 and 6 is actually a different outcome than 6 and 1. How many possible outcomes are there that give you 7 there?
6.
there are 6 possible outcomes, so what's the probability of rolling a 7? 6 over 36. So this is the probability of getting a 7. 6 out of 36, which if you reduce that fraction is 1/6. So that's what we're going to get up here as the probability of having rolled a 7, 1 out of 6. How about 11? What's the probability of rolling an 11? What are some outcomes that give me an 11 in this table?
5 and 6.
5 and 6. So this outcome right there gives me an 11. And what's the other possibility?
Wait. The other dice being 5 and 6.
Right. 5 and 6 or a 6 and 5. All right, those are my 2 possible outcomes that give me an 11. And so how many outcomes give me 11 in this sample space?
2 out of
2.
36.
Right, out of 36 total, so the probability is 2 out of 36, which if you reduce that fraction is 1 out of 18. So now the probability of rolling an 11 is 1 out of 18. So now we know the probability of rolling a 7, the probability of rolling an 11. How do we find the probability of absolutely anything else happening?
All the other outcomes.
All the other outcomes. How many outcomes did we not highlight here?
28.
Yeah. How'd you get 28?
36 minus 8.
Yeah. 36 outcomes in total. We've covered 8 of them as the 7 and the 11, and so the rest are 36 minus 8. That's 28 out of 36. If you reduce that down, what's that going to be? 14 out of 18, which is 7 out of 9. So the probability of anything else happening here is 7/9. So now we know all the probabilities that are possible in our particular game here. And now we have everything that we need, all the information, to set up the expected value. So what should I do now? How do we find the expected value? Now that we know the values of this variable and the probabilities of achieving the values. So right, step 1 is to multiply. So I'm just going to multiply straight across in each one of these rows. $10 times 1/6. Let's make 1/6 into an approximate decimal, 0.1667-ish. So when I multiply across, this is a good use case for a calculator here, we'll get $1.67 approximately. When I multiply $10 by 1/6. Then I'll multiply $10 by 1/18. Again, pull out a calculator for this if it helps, and I think it does. Okay, and then what about $0 times 7/9? Yeah, that one we can do without a calculator. Okay, so now we've multiplied across each value by its probability. So what do I do to get the expected value? Add these all together. So the expected value that I would get for playing this game is $1.67 plus 56 cents. That's going to be, if I added these right, 223. So there's the expected value for this game. The expected value of my winnings. So if I come to you and I offer you to play this game for $2 ticket, do you agree or not? If I charge you $2. No? Why not? I could, right. I could make 23 cents worth of profit. So there's a profit potential there. I would say that $2 is actually a good price for me if I want to play this game. Because I could actually I expect on average to make a profit. Even if it's only a 23-cent profit, I expect on average to make a profit. If I were to charge you $5 to play this game, then no, because I'm going to expect to make, even though there's a chance that I could win $10 and make $5 in the process, right? The chance is insufficiently likely such that on average I would expect to lose money. Right? So there we're finding that middle ground. We could win $10 or we could walk away with nothing, but when we consider the probabilities of each of these outcomes, we shouldn't pay any more than $2.23 to play this game on average.